And welcome to this lesson on graphing lines, which I've also titled Linear Relationships, because I think that's a very important concept for us to keep in mind. If you find this lesson helpful, please give it a thumbs up and subscribe to the channel for more math content, and leave a comment or question below and let me know what you think. I have had a cold for the last week or so, so forgive me if I sound a little bit congested. It is improving, but not quite there yet. We're going to work through this lesson with the example y equals negative 3x plus 5, and we'll use this example to really establish what it is that we're doing when we graph lines. So what are we looking at here? This equation relates the set of numbers for x to the set of numbers for y. So in other words, I could plug in different numbers for x, and when I do that, I will get a value out for y. And that set of numbers that I can use for x will be related to the set of numbers that I get out for y in a very specific way. This relationship will follow a specific pattern. And what I wanted to start with is just exploring here. So let's see if we can find the pattern that relates our x's and our y's. To do this, we're going to pick values for x and find the value of y that will make the equation true. And when we pick those values for x, a lot of times teachers will provide you with values and students don't necessarily know where those values are coming from. Essentially, we can pick any number we want. So any number you can think of, 0, 1, 2, 3, 4, 5, 100, 1/5, negative 0.25, like whatever number you can think of, you can pick. Now, some of those values are going to be nicer than others, and we'll kind of get to that at the end of the lesson. How can you pick numbers that are going to get you where you want to go in the easiest way possible? In other words, we're going to find possible solutions for an equation. So remember that a solution is what makes the equation true. So I'll annotate that there. Okay, so the solutions make the equation true, and those solutions are going to follow a particular pattern. That's what we're looking for. That's what the relationship is. So this does take some scratch work. So we have our equation y equals negative 3x plus 5, and we're going to pick some values for x. Now, for simplicity, I decided to pick 0, 1, 2, and 3. And you can pick anything you want. So you can pick negative values, you can pick only even numbers, you can pick decimals and fractions. Normally we don't, unless it was a word problem of some sort where we would want a specific kind of yuckier value. And we do some scratch work, and I want to be clear that this is the scratch work. So first, we'll take y equals negative 3, and we're going to plug in x is equal to 0. So I'll plug in the 0. And what you can notice here is so many skills from earlier in Algebra 1 coming into play here. So, evaluating, being able to plug in numbers, order of operations, all your signed numbers, all of those skills are assumed at this point. Negative 3 times 0 is 0, and 0 plus 5 is 5. So when x is equal to 0, y is equal to 5. Now, just to verify that that is a solution, remember the solution is the value of the variables that make the equation true. And this was my equation. If I plug in 5 for y and 0 for x, we end up with 5 equals 5, which is true. Now, I am not going to do that every single time. It's just when you plug in a value for x and you get the value for y that goes with it, if you go back and plug both of those values in, then you will get a true statement every single time. So therefore, when x is 0, y is 5, and I'll go ahead and on the right here, we have a table that organizes our results. So we have the column with our x values and then the y values that go with them. Looking at the next one, for the next one, we will plug in x is equal to 1. And so negative 3 times 1 is negative 3. And negative 3 plus 5 is 2. And then coming over here to the table, when x is equal to 1, y is equal to 2. Next one, we'll do x is equal to 2. And sometimes in the early stages of Algebra 1, you might be required to show this work. Sometimes you can do it on a piece of scratch paper off to the side. It's not super essential. If you've got certain kinds of calculators, you can just dump this into the calculator. So if you have a graphing calculator or you're familiar with the online calculator Desmos, you wouldn't need to show this at all. You would just simply put this in and it would spit out the answers and you could fill in your table. -3 times 2 is -6. And -6 plus 5 is -1. So when x is equal to 2, y is equal to -1, and we'll do one more. So we'll have -3 times 3 plus 5. -3 times 3 is -9, and -9 plus 5 is -4. Now, let's take a close look at this table here. What we notice is that my x's are increasing by 1. Okay, each time. And when I do that, my y values are decreasing by 3. And when I do this with my own students, I often will encourage them to look at the positive numbers. The negative numbers carry the same pattern. It's just a little bit harder for our brains to get around it when we're working with the negatives because it's we have to deal with the absolute values and we're moving left on the number line. But we can see clearly that 5 minus 3 is 2, 2 minus 3 is 1, -1 minus 3 is -4. And so forth. So this is what's known as a linear pattern. If you increase or decrease x by a very specific amount, so in this case, we're increasing by 1, but this would also be true if we increased by 2 or by 3 or decreased by 1 or by 2. As long as you're consistent with the increment in your x and you're not picking numbers in some hodgepodge way, you should see that your y values increase or decrease by the same amount each time. So this gives us a set of ordered pairs. So essentially we can take the table and turn the table into a set of ordered pairs where we have the x value and the y value that go together. So we have the 0.05, the 0.12, the 0.2, -1, and the 0.3, -4. And we can plot those on a coordinate plane. And I did this, like I have this nice graph here, so everything is like perfect. And if you look at that, you can tell first off that the points are not scattered haphazardly. It's not like we ended up with numbers all over the place. The numbers all seem to be lining up. So note that these points fall along a line. That's why it's called a linear relationship. So the words here matter. In the word linear, you will see the word line. So line ear, okay? And that is the word linear. And what it means is a particular kind of relationship between the x's and the y's that when we graph the solutions, they will form a line. In math, all lines are straight. So outside of math class, you might hear talk about curvy lines or a wavy line. That does not mean anything inside of a math context. So in a math context, lines are always, always, always straight. Okay, if it's not straight, we might call it a curve, or we might have another name for it for a different kind of relationship. Now, we picked 4 values for x at random, sort of at random. I just started at 0 and counted, but there are an infinite number of values that we could have picked. So like I said, you can pick anything you want. All of those values would have resulted in points along the same line. So let's say you just feel extra bold and you're like, I want to pick a really big value for x. Well, go for it, okay? So you've got y equals -3. We'll pick x equals 100. So that'll be -300 plus 5. So that gives me -295. And so the point 100 -295 would also have worked. You can pick negative numbers. Now, a lot of times students don't want to pick negative numbers because the arithmetic is a little bit more error prone, but sometimes negative numbers will actually give you better values than positive numbers that might get very big. So you have to count in the negative direction. What do we have here? -3 times -2 is +6. And 6 plus 5 is 11. So the point -2, 11 would work. And you can pick fractions, you can pick decimals, you can pick anything you want. So let's try 1/3. And -3 times 1/3 is -1. And -1 plus 5 is 4. And so we'd have the point 1/3, 4. And those points would work. Typically, we don't pick very large numbers because the numbers will tend to get very big, or we don't pick decimals and fractions unless we have a specific reason in a particular problem why we want to do that. So let's take a look at that. So to do this, I had to change the scaling on the graph, and you can see the original points that I had, and then we have these new points, and they're all kind of clustered up here because in order to plot this point, we had to extend our grid to go out to x equals 100 over there and down to -295. But what I want you to notice about this is that if we drew the line, they would still all be lined up, okay? And so that point that's way off still is on the same line. It's still lined up with all the other points that we have on the coordinate plane there. Now, how can we represent these infinite solutions? So we have established that there is this relationship and that we can pick as many values of x as we want. But right now, we've just been plotting them as a bunch of dots. Well, we do a couple of things. One is we draw a solid line to fill in the spaces between our dots. The dots are points on the line, but we also know that there's an infinite number of points in between the points that we picked. This indicates that all the points in between our dots are also solutions. And we don't want to confuse our dots with all the points on the line. Many times in my classes, I've said pick a point on the line, and my students home in on the dots. Any place in between the dots also constitutes points on the line. And then we place arrows at the ends of the line, and that indicates that the line continues off the coordinate plane to all the points that we can't see. So in that last example, we had several dots that were together and then one dot that was way off. We don't necessarily want to have to draw the coordinate plane big enough to see that. So what we do is we draw arrows at the end, and that just indicates that the graph continues on. And so what I did here was I did all of this in different colors. So we have the original 3 points or 4 points that we plotted in green, connecting them with the line. Now, those extra points that I did, the only one that shows on this particular coordinate plane is the 1/3, 4, okay? And that one is done in red. The other points are all off the edge. So the -2, 11 is right up there. The 100, -295 is way down off the edge of my screen here. So we color in the line. So any point on that line is a valid solution. And then we put those arrows at the end, and that signifies, hey, this line keeps going. Now, I want you to notice just one thing before we move on from here. And that is that the idea that it's not just the dots. So if I look right here, I'm going to put a dot here. My pen is probably going to give me a hard time about it. There was no dot there before, but clearly the point 4, -7 is on that line. Just because there's no dot doesn't mean that it's not a point on the line. All right, and that's what the solidness of the line does. We're basically coloring in, hey, everything in between also works. So let's do another example. This one, the equation, we'll use x minus 2y equals 2. And I have picked the values -2, 0, and 2 for our values of x. So let's go ahead and take a look at that. So we've got -2 minus 2y equals 2. And if you need to, you can change that subtraction over to a plus negative. We're going to try to solve for y. So that means I will add 2 to both sides. -2 plus 2 is 0. That's why that cancels out, leaving me with -2y is equal to 4. And dividing both sides by -2, we get y is equal to -2. Now over here, we're going to build ourselves a table. And now we know that when x is -2, y is also -2. Next one. 0 minus 2y equals 2. Well, 0 minus 2y is just going to leave us with the negative 2y. Divide both sides by negative 2, and we get y is equal to negative 1. So when x is equal to 0, y is equal to negative 1. And last one, we'll go ahead and plug in x is equal to 2. So 2 minus 2y is equal to 2. We'll change that to the plus negative in case that helps. We're going to subtract 2 or add negative 2 to both sides. 2 minus 2 is 0. Again, y that cancels out, leaving us with negative 2y. 2 minus 2 is 0. And dividing both sides by negative 2, 0 divided by negative 2 is 0. And so when x is 2, y is 0. Now take a moment and observe the pattern. Here we are increasing by 2. So my x's are increasing by 2. Like put that on here. Increase by 2. And over here we are increasing by 1. And that pattern seems to hold. Then on our coordinate plane, we'll go ahead and plot those points. So negative 2 is a dot right there. 0, negative 1 puts me right there. And 2, 0 puts me right there. And you can see that those 3 points all line up. And so what we'll do is we'll connect them and try to make your lines go to the edge of the visible grid. I've had students do things like this, like they'll plot 2 points and they'll just do the line like that. And technically there's nothing wrong with that because it's showing where the line is, but it is a little bit awkward. And later on in algebra, you'll do stuff where you have to use the graph to maybe find a point of intersection. And if you don't use up the coordinate plane that you have, it can just make that a little bit harder. So you can grab a ruler or a straight edge and you want to use the space that you have on whatever coordinate plane you have, like size it to scale. When I first started doing these, I just remember feeling like, oh my word, I'm doing like really cool math now. Now I've finally arrived. I am graphing lines. All right, so the key idea here, the graph is the visual picture of the points that make the equation true. In other words, it's the picture of the solutions. Graphs will follow specific patterns, okay? In math class, I mean, you will occasionally get like what's called like a scatter plot with things that are genuinely scattered. You can do scatter plots that have patterns as well, but the crux of a lot of your math work will be exploring those patterns. We start in Algebra 1 with the linear pattern. So the first pattern you encounter is the one that we've just looked at. And we use that to explore lots of features of graphs and what they can do. In future math classes, and sometimes beginning in Algebra 1, you will explore other types of patterns. So we take this linear pattern and we just explore it, and we do a deep dive into that linear pattern and what the graphs look like and the strategies for graphing. We look at fast ways to graph them and what we can do with the graphs once we have them. And then we extend that to other types of patterns. The concepts you learn with lines will transfer over to those other relationships. Thus, it is important to master lines well. Okay, it's not the time to start taking shortcuts on your math. Now, how do we choose some points? Some points come out nice. So, for example, if this here is your equation, y equals 1/2 x plus 5, and you choose x is equal to 4. So you got 1/2 4 plus 5. Well, 1/2 of 4 is 2, and 2 plus 5 is 7. And so you got this like nice point when x is 4, y is 7. And some points come out yucky. So that's a very high-tech math vocabulary word there with yucky. And so if you were to pick 3 for that, then you realize, ooh, like half of 3 is 1.5. And you might think, well, that's not that yucky. No, I mean, it's not that yucky, but it's also not the greatest. You'd have to estimate where the 6.5 is, and we'd like things to come out nicer. You will get better at choosing good values with practice if you take the time to look for patterns. So an experienced person graphing lines will just have a sense of what numbers work well. 0 often works well. 1 is very popular choice. 2 is very popular. -1, often popular. -2, those tend to work well. Numbers like 17, not as well, and you will get better at that with practice. I'm not going to give you any shortcuts because you will learn it better if you just explore on your own and see what works. Was this video helpful in graphing lines? Give it a thumbs up and subscribe for more math content. And thank you very much for joining us. I'll see you in the next one.